Good morning, everybody. Welcome to another nice day of chemistry. Start with some green check marks, please, and then we'll get going. Thanks very much, guys. Last day, we kind of went through the different types of chemical reactions. So we had synthesis, decomposition, single replacement, double replacement, neutralization, and combustion. So the 6 different types of reactions. I left you guys with the learning guide sheet, which had about 20 or so examples, and you were asked to identify the examples as to which type of reaction there were. And of course, you guys have the answers there for all of these, so I'm not concerned about that, but I wanted to make sure that you guys didn't have any questions, or maybe there's an equation you looked at where you're kind of like, wow, this one didn't really make as much sense as the others, or really confused as to how this one was labeled as this. So if you guys have any questions from, I guess, 6.1 from the learning guide, or anything in chemistry for that matter, just any of it. Okay, so we'll do some examples to start, if that works, Kyla. And Costin has something specific. Now, I kind of just abandoned you guys at the end and didn't give you much time to go through these, so. Can you do some where you find out the Roman numeral? For sure. The multivalent metals, we can find some of those. All right, so this is on page, I don't have page numbers. That's disappointing. So 6.1 practice, the top of the practice section is for you to look at all the different types and just kind of summarize them, similar to what I did in the notes last day. So a synthesis reaction, what does that look like? Give an example. So we went through a lot of these in class. Costin, I'm just looking at your message. Is this the one you're talking about, or is it the one from down below? Yeah. So these are, if you look at the notes last day, I'll just jump back. Maybe I can find the notes from last day. The notes from last day had the tables that are almost identical to everything here. So for each of the reactions, we looked at something like this. And this is essentially what the first question is, Costin. So I'll definitely go through the second part as well, but just so you guys get a bit of an idea of what we're looking for there. So the general equation would just be, you could use letters X's and Y's, or A's and B's, or you can use little pictures if you wanted, it doesn't matter. And then a specific example, so sodium and chlorine combined together to give you sodium chloride. This is what that first part of the practice was all about. So for a synthesis reaction, you have 2 things. They come together to form a compound. The example we used in class was the Na and Cl. Together gives us NaCl. So that's kind of the first one done for us. Let's look at the next one. It'd be great if the computer was working. All right, so a decomposition. Now we don't have anything for this. We need to just, come up with it. And of course we looked at something similar in the notes yesterday, but a decomposition, if you think of the word decomposition or decompose, is where you take something and you break it down. Decomposers like bacteria, fungus, things like that, take like a dead tree in the forest and they kind of eat away at it and break it down into dirt or soil. And that is what a decomposition reaction in this context looks like as well. So decomposition is going to be something breaking down. So you're going to always have to start with a compound. Into 2 or more elements. So if we start with like a compound, it breaks down, we end up with two or more elements. So a general equation. A general equation doesn't need to have chemicals in it or elements from the periodic table. We can just write it as a general equation. So let's write something like AB. The compound AB is going to react, and that's what the arrow means, is there's some sort of reaction occurring here, to produce two things. And what did we start with? We started with A and B. So we separate two things with a plus sign. That indicates that there's more than one thing there. And then the example. The example that we did last day and we're going to do today is, maybe that's not a great example. Let's go with an easier example. Maybe we can take water, H2O. That's a compound, molecule, and it's going to react to produce hydrogen gas and oxygen gas. And you could have picked any substance. So we could have had, I think the one we used in class was NaCl. It reacts to produce, you break it down into sodium and chlorine. So we had two separate things. They're breaking down to become individual things. So that was the idea for all of these first ones. And you can just use the ones right out of the notes that we did last day. That's completely fine. So we had single replacement, double replacement, neutralization, and then combustion. And then question number 2, we didn't have an opportunity to go through, but we can right now. So if you haven't done question number 1, I encourage you to go back, and you can either go into the course, and all of those little summaries exist in the course, or you can just go back and look at the lesson from last day. Or what I can do, it might be even easier, is I will post up the notes from last day, the PowerPoint, and I'll just put it right into the course. And that might, if you still have to do number 1, it might speed things up a little bit for you. So we'll do that for number 1. Now let's go through some of number 2 right now, and it asks you to balance. But for now, we're not going to worry about balancing. If we have lots of extra time, maybe we will. But essentially, it's just going to take a lot of time. I mean, if you're good at balancing, each question only takes a couple seconds. But it's just a bunch of extra questions that we probably don't need to do right now. So we need to identify each type of reaction, and that's all we're going to do. So did anybody run into problems with any of these? Did anybody do any of these? Does it make sense for me to go through a few? I mean, if you haven't looked at the different types, then me just doing them might not be extremely worthwhile. But okay, I'll do a few, like 5 or 6 of them. All right, so when we are doing these types of questions, we need to look at what we start with and what we end with. And then if we can kind of simplify it down and lose the numbers and like the brackets and the polyatomics and all that confusing stuff, we can just simplify it just right down to what's actually going on. Sometimes, you know, we can get a better grasp on things. So H2O2, that's hydrogen peroxide. Not that you need to know that, but that's the experiment that we did last day, and we'll do it again a couple times today. Hydrogen peroxide is going to break down into 2 different things. So the idea here is I'm starting with one thing. And then I end with 2. So when I look at the different types of reactions that I had from last class, I guess I could jump back into that presentation I had. I'm looking for a type of reaction that began with one compound and ended with 2 things. And if I look through all of the different types, this starts with 2 and ends with 1, so that's kind of the opposite. The decomposition starts with 1 and ends with 2, so that's looking good. And then this one starts with a compound and something by itself and ends with a compound and something by itself. So that's single replacement. That's not what we're looking for. Double replacement starts with 2 compounds, ends with 2 compounds, and then acid-base neutralization and combustion are fairly unique and a little bit maybe harder to recognize. So the one that kind of matches the best is this one, where you started with one thing, a compound, and then it broke apart and you ended up with two separate things. And this is called a decomposition reaction. So if I go back, I need to identify it, and it says I can use DEC for decomposition. So I have enough room, I'll write it in. All right, so that's a decomposition. I start with one thing, it falls apart and breaks into two separate things. Maybe a bit confusing because it's not just breaking into H2 and O2, kind of like water would. It's breaking into water and oxygen, but you get the idea. All right, so that's the first. Are we all right with that? Any questions on the first one? Something that maybe you didn't understand or was maybe a bit confusing about that? Are we all right to move on to do a few more? The answer key says double replacement for the first one. That would not be a good thing. Although it wouldn't be the first mistake I've seen in an answer key for these course questions. Number 2, types of chemical reactions. It does indeed say double replacement. So that's definitely wrong. Keep you on your toes though. Hey? So this is a decomp, or DEC. Thanks for pointing that out, Leeds. The learning guides are, they're made by humans and there are mistakes in them. The math and science 8 ones that I use are terrible. I'd say like 30% of the answers are wrong. The science ones generally are a bit better. There's usually 1 or 2 wrong answers for an entire learning guide, which isn't exactly excusable, but it is what it is. All right, so other than the answer being wrong for the first one, there we go. The second one's it's a tough one. I'm just going to throw that out there. You're starting with a compound and a compound, ending with a compound and a compound. So you could have a double replacement, you could have a neutralization, or you could have a combustion. And it just so happens that neutralization reaction is just a very special type of neutralization reaction is a very special type of double replacement. So the reason it's special is that you're starting with an acid. An acid is anything that starts with H, and then a base ends in OH. And if you recall from last day, if I have HOH, together HOH can also be written as H2O. So that is just water. So when we have an acid and a base, they mix together to produce water. And then the other thing, the NaCl is called salt, whatever it is. Most ionic compounds are referred to as salts. So yeah, it's a neutralization reaction for sure, essentially a special type. One thing that will make the rest of this question a little bit easier is when you see water, H2O being produced, there are 2 types it could be. Number 1, it could be a neutralization, and the second thing it could be is a combustion. 99% of the time. The first example is kind of the exception to it, but generally speaking, if you have a compound and a compound and produce a compound and a compound, and one of the products is water, you're pretty good chance it's either going to be neutralization or a combustion reaction. In this case, it's a neutralization. All right, so that's the second one there. The third one it looks a little bit different than the other ones we've done thus far. And you can see that the third one, it has this element by itself. That aluminum is just kind of hanging out there by itself. And then the other thing is a compound. I have NiBr2. So we have something by itself and a compound. Okay, maybe I'll just go back to the notes. I feel kind of like I may be overdoing it, but we'll go back and we'll look through this. So we have something by itself and then a compound. That's what we're looking for. So that would be like, A and BC. So this is the situation we have. right here in a general terms if we're going to classify it. We have a compound, AB, and then plus C. And the C is going to take the place of one of the elements in the compound, and it's going to kick it out. So this is a single replacement. This is the reaction that we did yesterday with the copper 2 chloride, that blue liquid, and we put the aluminum foil in it. And the aluminum dissolved in the solution, and it kicked out the copper. And actually I left it. Normally I clean it up, but I left it here. And you can see that, maybe you can't see very well, the liquid isn't blue anymore, and in the bottom it's all this copper. When we go to switch to the other camera in a second, I'll bring it back out. So all of the copper 2 chloride, it took all of the aluminum and dissolved it all. So now the solution isn't copper 2 chloride anymore, it's aluminum chloride, and then we have the copper kind of hanging out by itself. All right, so it is a single replacement reaction. And we'll just call that SR. And what's happening is this aluminum's a metal. So in the compound, it's going to replace the metal, because we can't have the metal replace the non-metal. If the metal replaced the non-metal, we'd have two metals. We'd end up with, I've written something like this before, we'd have NiAl. And those are both metals, so we can't do that. So that can't work that way. So what's happening is the metal is replacing the metal, and it's going to kick it out. So now the nickel's by itself, and then the nickel was combined with the bromine, but now the aluminum is going to combine with the bromine. And that is a single replacement. Are we doing okay? Are we kind of maybe getting it a little bit better now? A little bit more confident with these sorts of things? I know at the end of last day I just said, these are all of them, and I didn't give you any examples, and I just kind of left you, which wasn't fair. But I was hoping you'd have an opportunity to kind of go through these maybe a little bit. How about letter D? Does anyone want to take a guess as to what letter D is? Starting with two things kind of hanging out by themselves, and then we end with a compound. So what's that going to be in terms of our 6? You don't know the names of the answers. Oh, I see what you're saying, Costin, because you'd have to memorize, single replacement, double replacement, combustion, decomposition, synthesis. Yeah. Good news is on a test, it's likely going to be multiple choice, so they'd be written for you. I don't know if that makes things any better. Just thinking in the data booklet, there's no reference to any of the types of reactions, so that isn't going to really help us much, unfortunately. So yeah, it's just one of these things where you're going to have to remember what they are. A little bit of practice will help for that, Costin. I mean, you just saw them for the first time yesterday. Anyone? Letter D. Want to guess as to what that might be? So Leeds is going synthesis question mark. I like your guys' question marks. Like, I'm not entirely sure, so I'm going to throw a question mark after it, and then maybe somebody will agree with me, like Kyla to the rescue. And then somebody else might put synthesis with no question mark, and everybody agrees. Yeah, you're right, Leeds. You got to have confidence in your answers, Leeds. All of you guys, for that matter. Yeah, it's a synthesis reaction. So we'll just write it as SYN. We start with two things, and then they combine together to produce something, and that something included the two things we started with. So when we end with one thing, it has to be a synthesis reaction. There's no way around that. Okay, I feel like we're on a bit of a roll here. Let's keep going. Let's do the last two here, and that'll, I think, give us all 6 in the first 6 questions. All right, so the next one here has Ag, so that's silver nitrate and potassium chloride, produces silver chloride and potassium nitrate. What's going on here? So if we look really carefully, let's just follow one element. So I'm going to just randomly pick the first one. I guess that's not so random, that's just picking the first one. So Ag, silver. Silver was combined with the NO3 group, that nitrate group. And what happens to it? Let's find silver on the product side. Now silver is over here, And it's no longer with that NO3 group. So the NO3 was here with the silver, but now the NO3 is over here. So it looks like they're kind of switching partners sort of thing. If we follow the potassium, the K started with the chlorine, and now the K is with the nitrate. And then the chlorine's kind of the last one here. The chlorine started here, now it's with the silver. So they're essentially swapping partners. The compounds are switching. And this is what we call a double replacement reaction, where a single replacement we looked at up above in letter C there, where the metal kicked out the metal. This is the exact same thing, except instead of the metal kicking out the metal and the other metal just existing by itself, they're just switching partners. So they're essentially just swapping. The silver was with the NO3, now the silver is with the Cl. And again, we can't switch so the silver and the potassium are together, so we won't ever end up with over here AgK, because we can't have two metals. So this is the only possible thing that can happen. We can only switch the metal with the metal. There's no other possible combination. Knowing this, knowing that we can't have two metals. So with that in mind, that's the only possible outcome we could have there, would be them just switching. The last one is the kind of the special case. As soon as I see water, a little light bulb needs to go off in my brain, and I say, okay, I have water, and as I said up above here, the water is one of two things. This is either a neutralization reaction or a combustion reaction. A neutralization reaction starts with an acid and a base, which is an H and an OH. And I don't start with an H and an OH here. I don't have those at all. But I do have this hydrocarbon. There's my hydrocarbon and oxygen. So this is definitely going to be a combustion. And a combustion reaction always produces CO2 and H2O. It doesn't matter what hydrocarbon you start with, you're always going to produce CO2 and H2O. So how do you know, Mr. Borden? Well, I know because I've seen it 100,000 times. How would you know, Costin? That's a great question. Notice when we looked at kind of the general form here last day for the combustion type reactions, even in the kind of the general equation, so not a specific example, but the general equation, normally it'd be like, A and B and C and D. The general equation for combustion has CO2 and H2O. That's what's produced. It doesn't matter what hydrocarbon you start with, you're going to produce CO2 and H2O. Anytime you burn a hydrocarbon in the presence of oxygen, you're going to have CO2 and H2O. So even for the general equation, not a specific example, just generally speaking, these are the things, CO2 and H2O, that you're going to produce 100% of the time. It doesn't matter if it's CH4, C2H6, C10H53O2, you're always going to produce CO2 and H2O. That's just what happens. So these are really, when you're going through them, they're really obvious. So let's maybe just look at the list and see if we can find another example, and you can perhaps see why they're a little bit more obvious, because they always look exactly the same. So we've got all 6 there. Let's find another combustion reaction. If you guys see one, just throw it into chat. We did those. See one there. So up at the top, we have letter M here. We have CO2 and H2O being produced, and a hydrocarbon to start with oxygen gas. So anytime you burn something. So that's definitely combustion, letter M. If I keep going, is there any others that end in CO2 and H2O? Where are you, cursor? Q. Here's another one, letter S ends in CO2 and H2O. That's going to be combustion. Letter X ends in CO2 and H2O. And notice they all start with something different. I have C8H18. I have C6H12O6. But what's being produced, or the second part of the equation, is always going to be exactly the same. So the amount of carbons and hydrogens is going to change, but the products are always going to be the same. You're always going to end with CO2 and H2O. You also have oxygen gas, O2, as a reactant. So how do you know, Costin? They kind of all look the same for combustion especially. And it just comes with a bit of practice, bit of exposure. I mean, yesterday was the first, or Tuesday, I suppose, was the first time any of you had likely ever heard that there was different types or classifications of reactions. It's the first time you've been too exposed to it. You know, now you'll have an opportunity to hopefully go through the remainder of the sheet and see if you can start to, you know, experience a bit more and kind of get the hang of what's going on. And after a bit of practice, I have confidence that you guys won't be lost on this stuff anymore. Does that kind of work for now? Do we want to do a few more, or do you think it would be good if you guys had an opportunity to look at them now and try some on your own? A few more, please. Do more, do more. Okay, for sure. All right, let's just, this is where we're at, S, T, U, V, W, and X. Let's do a few more of these. Okay, let's just, we've done S and X, so this is combustion, and this is combustion. So we can write those in. Let's look at T. T, I start with one thing, NH4NO3, so that's kind of like AB, and it reacts to produce A and B. Not exactly, but kind of, if I had to generalize it, that's kind of what's going on there. Starting with one thing, ending with two. If I start with one thing, it breaks down into two things. Type of reaction am I dealing with? If I'm going to do more, you guys are going to have to help me. Start with one, breaks down, end with more than one. What are we going with? We've already done one. In fact, we've done a few of them. So a single replacement would look like this. I'd have AB and C reacts to produce, we'll go with AC and B. Gonna run out of room? Nope. So a single replacement doesn't have the same structure as this particular question. This one starts with one thing and it ends with two, whereas a single replacement has, you know, starting with two things. So it's definitely not going to be a single replacement. Decomposition, that kind of fits the decomposition, but you're right, and this is a tricky one because what's produced isn't just, you would expect it to be like, we had NaCl was the example we used in class, and then just Na plus Cl with two separate things. But that doesn't happen here because we're starting with two polyatomics, and it's just really confusing stuff. You are right though, Costin, it is a decomposition. It's just kind of a trickier one, just because you're starting with NH4 and NO3, so there's a lot more elements there to deal with. All right, letter U. U. Okay, I'm gonna kind of just try to figure out the general idea of what I have here. So I look, I have aluminum and carbon, so that's like a compound. And then I have hydrogen and oxygen, so that's another compound. And these are going to produce, you know, the carbon was with the aluminum, but now the carbon's with the hydrogen, so this would kind of be like, what am I going to go with here? CB and AD. Again, a little bit more complicated, but I'm starting with a compound plus a compound, and then I'm ending with a compound and a compound. Maybe what might be worthwhile until we've seen a lot of these things is just when you get to a question, maybe even just highlight the plus signs and then the arrow to see, you know, am I starting with two things and ending with one? Am I starting with two and ending with two? Am I starting with, you know, one ending with two? And that might just make it a bit easier to kind of narrow down the choices perhaps. So here I'm starting with one compound plus another compound produces a compound and another compound. So it's either going to be a double replacement, It's going to be a neutralization or it's going to be a combustion. Now, I've identified my combustions already because those always produce CO2 and H2O, and that's not the case here. I don't have that. And then the other special one is the neutralization that has to start with an acid and a base and end with water and a salt. And I'm not producing water here. So this is a double replacement. This is essentially where they just switch partners. The partners just swap. All right, letter V. I'm starting with two things. And I'm ending with one thing. So it's a little bit more difficult example of a, we want to take a shot at that one. Starting with two, and then I end with one. So there are two things coming together, ending with one. Is it wrong that I hate that you put a question mark after that, Eric? Yes, of course, you're right. Synthesis. Yeah, it's synthesis. So you're starting with two things, they're combining together to produce one. I start with two, end with one. That's kind of the general idea behind a synthesis reaction. Letter W. All right, I have PbNO3. So I have two things, again, to start, kind of like AB. And then I have an arrow. And then I have a little A, a little B, and another little B, I guess. They both have the oxygen. Again, it's a little trickier example, but I'm starting with one thing and ending with multiple things. So by definition, the only type of reaction that starts with one thing, what's the only one that just starts with one and ends with more than one? I double dog dare somebody to put in the answer without a question mark after it. Thank you, Eric. Leads. Yeah, you guys are right. So it's a decomposition because decomposition is the only one that starts with one and ends with multiple things. Let's maybe, just thinking I could write down just a kind of like a summary. If you guys want to jot this down, you can, just to kind of simplify things perhaps a bit further. So our different types of reactions were, we had a decomposition was the first. Then we had a synthesis. We had a single replacement. We had a double replacement. And then we had neutralization. And then a combustion. So I know we have these in the notes, but we don't have them perhaps all in one spot. So decomposition is where I start with something like AB, and I produce two things, an A and a B. So that is what your decomposition looks like. The example we just looked at was like ABC produces A plus B plus C, but it's just one thing breaking down. So that's one. Synthesis is where I have something like A and B. So I'm starting with two, and I end with one, AB. Single replacement is where I have a compound and something by itself, and then that something by itself kicks out something in the compound. So in this case, the C replaces the B. A double replacement is where they swap partners. I guess I could have color coded this. That might have made a little bit more sense. Neutralization is a special type of double replacement. Where I have that H and the OH, and then they swap partners and I end up with HOH. And the HOH is just the same thing as water, so we could just write it as H2O. I'll just move that over. No, we're good. All right, so that's a special type. And then combustion is where you have the same thing always. You have a C and an H, and they're going to have some numbers down here. You're always going to have oxygen, and it's always going to produce CO2 and H2O 100% of the time. So the C and the H, sometimes there might be another oxygen tagged on here with a bunch of numbers next to it, but generally speaking, you have C and an H, and then what's produced is always going to be the same. So that's just kind of like a brief summary of all those different types. Hopefully, you know, the idea is that they're not always going to look exactly the same, but you should get a sort of a general idea of what they're going to look like. Does anybody have any questions there? I don't have any issue with, I'm going to go through the next set of notes on reaction rates. And then, you know, we can come back and look at this stuff again next day. And I think it was Josh or Jonah, sorry, asked about the multivalent metals, so I can do those as well just in a second. So don't think that I haven't forgotten about that. I'll get back to it. Does anybody have any questions before I move on? We can spend more time on this next day for sure. We don't have to just forget about it like it's just done forever. How about I leave you guys with this little chart, and then, you know, you can attempt the rest of the questions in number 2 there. The stuff we're going to learn today is, I think it's pretty straightforward. Generally speaking, students don't have too big of an issue with it. So if you can get, you know, the different types, you should be doing okay. All right, so rate of chemical reactions is important. It's important to be able to control how fast or slow a chemical reaction occurs. And we don't always want reactions to occur really quickly. Can anyone think of a chemical reaction that happens that you don't want to happen quickly? Or is there any kind of chemical reaction you can think that you might want it to take a really long time to happen? It's kind of funny, you guys interact with chemicals all the time in your everyday lives, but you don't really think of them as chemicals. You know, everything's made up of chemicals essentially. Sometimes you want a reaction to happen really fast, and sometimes you want it to happen slowly. All right, so what's something we want, a chemical reaction that we want to happen really slowly? And you guys, you don't want milk to burn fast. Like when you're cooking, Jenna, is that what you're referring to? Yeah, when you're cooking. So cooking and food in general is a really, really good example of all of these things. So when you're cooking food, sometimes you want the reaction to happen really slowly. In the case of burning something, you might not want it to happen at all. What's some other examples of food? You have, I assume you all have this in your house. I would be quite surprised if you didn't. Something you have in your house that prevents chemical reactions from occurring quickly. Kind of weird to think of it this way, but once I tell you what it is or you come up with it, you might be like, that makes sense. It has to do with food. Something in your house, yeah, Eric, fridge. So, you know, food, if I leave food out, it's going to break down. It's going to decompose because bacteria and stuff's going to eat it. There's chemical processes happening there. So why do we put food in the fridge or freezer? Is to prevent chemical changes from occurring, to slow down the decomposition of the food or fruit or potatoes or whatever you put in the fridge. So those are examples of why you would want reactions to happen slowly. You're not going to be able, well, I shouldn't say that. It's going to be difficult to avoid food going bad, like fresh food. So you put it in the fridge or freezer to slow down that reaction. What about a reaction taking place quickly? Can anyone think of something that you might want to happen fast? And cooking is a great example of this. We have these proteins in food. We want the proteins to change quickly so we can eat them. We cook them. So that's a great example. Any other examples of a chemical change you might want to happen fast? The one that, go ahead, Costin, I'll let you put it in if you're going to attempt something here. But the one I always think about is when I take, like, if I have a headache or something. And cooking meat, that's a great one. I always think of eggs because I don't know. It's easy to think of an egg cooking. It goes from this clear thing to a white thing, but meat cooking, same deal. Yeah, you want that to happen quickly. You don't want to cook your food for days. But if you take like an Advil or something because you have a headache, those chemicals are released into your bloodstream. You want that to kind of happen fast. You don't want it to take, months. You want, kind of quick relief of headache or whatever sort of symptoms you may have. So to make a reaction happen quickly, we're going to look at all of these in depth. And the opposite's true of each of these, but just to get you started, if we increase the temperature, the reaction will happen faster. If we increase the concentration of the reactant, so if we have more concentrated reactants, it should happen faster. We can increase the amount of surface area, and then we can add a catalyst, or the opposite of adding a catalyst is something called an inhibitor. And because I always talk about cars, when I always get to this point, when we want a reaction to happen slowly, I have old cars and they rust, and that is a chemical reaction. It's the iron in the car reacting with oxygen in the air, and I don't want that to happen quickly. So I do everything I can to prevent that reaction from happening at all by painting and waxing and things like that, or just making it happen as slowly as possible. So that's another example of a reaction that you might want to happen quite slowly, is your car rusting. So the opposite's true. If I want a slow reaction, I can decrease the temperature. I have batteries at home. I have 2 small kids, and everything that they have in this entire world has batteries and makes noise and has flashy lights on it. Drives parents crazy, but I take my batteries when I'm not using them. I put them in the freezer. Why? Because batteries have chemicals in them, and that chemical reaction is producing voltage. If you put your batteries in the freezer, it slows down the reaction, and they're going to last for longer. Back in the day, when I was a young kid, when we used to take pictures, we had film that went in a camera, and a lot of people would store film canisters in their freezers to make the film last longer, so it wouldn't be exposed and keep your film better. You can decrease the concentration to slow things down. You can remove the surface area, lower the surface area. The surface area is harder to do that. Jesse, are you doing the film thing? Is that what you're agreeing with, or the battery thing? Sorry, I didn't see you put it in there. Film. Yeah, so if you have a film, it's kind of weird how you have these niche, people that take pictures with film still. It's kind of like records are having a huge comeback right now. I'm sure eventually film and taking pictures on film will, be just as popular as digital cameras eventually. Maybe not as mainstream, but for kind of artistic reasons, I can totally see why film would be an interesting thing. I don't know how this is going to play. Skaters film with a VX, and it takes film. There you go. So if you're doing some, video to get that kind of look. These, if you believe it or not, on my screen run really smoothly, but why do we care how fast a reaction occurs? So on the left, this is a watermelon being dropped from, I think it was like 2 or 3 meters, and the airbag on the left is inflating on time, and you can see how the watermelon kind of gets cushioned. And then on the right, we have an airbag inflating 1/100th of a second late, and you get the idea. Obviously, the watermelon is a bit of an analogy for your head. So, yeah, if you have an airbag that inflates just a second too late, your head's that much further forward, and basically your face is going to be the recipient of an explosion, and there's no other way to put it than that, which isn't good. So yeah, that's why it's important for these reactions to happen at the right rates. And it's really maybe not funny, but one of the people who works here, Mrs. McIntosh, she has a Subaru, and we were just talking the other day, we were going to a field trip or something, and she said, oh, I can't drive anyone because there's a recall on the airbag in my car and nobody can sit in the front seat. And then my brain immediately goes to, you know, this scenario where you have this airbag inflating just a fraction of a second too late, and I'm like, yeah, you know what, maybe I don't want to ride with you. Not that she's a crazy driver or anything, but you never know. It's a scary world out there. So if you have a car that's made in the kind of middle 2000s, there's a big recall on airbags, and I don't exactly know what was the problem. I think they don't inflate at all when they're supposed to. But anyways, airbags are really a good example of a reaction that you want to happen extremely quickly. And airbag isn't what a lot of people think. It's not a canister of compressed air that, you know, gets released and inflates the airbag. That happens too slowly, if you can believe that or not. So if I had a canister of pressurized air and I tried to release it into a bag, it just happens too slow. It doesn't happen fast enough, and in an accident your head would hit the steering wheel or the dashboard before a canister could inflate the bag of air. So what they use is something called sodium azide, and basically when you have a vehicle that, you know, experiences some sort of shock, there's a sensor, a chemical reaction occurs with the sodium azide, and it produces a bunch of nitrogen gas very, very quickly. And that nitrogen gas fills up the airbag. And that's how your airbag works. All right, so temperature, you guys are well aware of what temperature is, but it's kind of sometimes good to take a step back and think about the science definition of temperature. So temperature is the measure of the average energy of molecules. If you have molecules that are moving really fast, then they have a higher temperature than ones that are moving slower. And then you can have your states of matter. So if you slow them down enough, they turn into a solid. You speed them up a little bit more, add some energy, you have a liquid. Speed them up more, they turn into a gas. And the idea here is if you have chemicals mixing together, if they're moving really slow, they're not going to bump into each other very often. And essentially when they get close to each other and they bump, that's when they're going to react. So if they're moving slowly, they're not going to bump into each other. But if they're moving fast, they're flying around, there are going to be lots of collisions. The more collisions means the faster the reaction is going to occur. And sometimes we want reactions to happen slowly, so we use things like refrigerators and whatnot. And then sometimes we want reactions to happen fast, and you guys use the exact examples I have here. So cooking food, we don't want that to take a long time. So I have a few kind of demonstrations that I wanted to do today, just with the same stuff as we used last day, that hydrogen peroxide. So maybe I'm going to go through all these and we'll see how much time we have. We should have enough time, but I just want to make sure we get through the notes, and then we'll do some examples. So I have over here next to me, I'll just bring it into this shot. I have some hydrogen peroxide, and there's two beakers here. One's in an ice bath, so I'm cooling it down, and then I have another one on a hot plate. So it's the same stuff. One's hot, one's cold. We'll add the potassium iodide to it and see which one reacts faster, essentially. And the second one we're going to look at is concentration. So concentration, the best way I can think of describing concentration is talking about iced tea. When I was a kid, I'd get home in the middle of summer from like playing basketball or something, and I'd mix up some iced tea. We had some iced tea powder, hot chocolate maybe. You can make iced tea that's like super, super sweet, and I don't like really sweet iced tea. So that would be really concentrated. If you put too much iced tea powder, you mix it up, and it's just like super, super sugary. It's really concentrated. So to make it less concentrated, you just kind of add a bit more water, and then it gets less concentrated. Or hot chocolate, it's kind of the opposite of that. I don't think I've ever had hot chocolate where I'm like, well, this is way too sweet. I hate hot chocolate that's not sweet enough. So, I mix my hot chocolate, it's not sweet enough, I add more powder, I increase the concentration. So the amount of water stays the same, but I've added more powder into it. Your sister would eat the powder? I'm not gonna lie, I've probably had a few spoonfuls of iced tea powder in my day. Also done that, but yeah, so she ate cinnamon too. That's probably not as advisable as the iced tea powder. Kind of spicy, that cinnamon. She almost died. I don't know why I'm laughing at that, but yeah, cinnamon, not fun to eat a big spoonful of that. Wouldn't be good at all. So the higher the concentration, the faster the reaction occurs. It just means there's more stuff there to react. So the example, I do have it here. When I talked about hydrogen peroxide the other day, I said, do you have hydrogen peroxide in your house? And this is what a bottle of hydrogen peroxide in your house probably looks like, something like this. They put it in this brown container so light can't get in. And this is from just like a drugstore, wherever you guys buy your hydrogen peroxide. This is 3%. So if I took this full bottle, 3% of it is actually hydrogen peroxide. The rest of it is just water. They just dilute it. And the reason for that is, hydrogen peroxide is pretty nasty stuff. So this special super duper good hydrogen peroxide that I buy, this is 29%. So that means this much of the container, a third-ish, is hydrogen peroxide, and then the top 2/3 is water. So if you can compare 3% and then almost 30%. So this is 10 times the concentration of the stuff you can buy in a store. So there's just a lot more hydrogen peroxide in here. It's still diluted in water, but it's just a lot more concentrated. So the more concentrated, the more molecules are there and the more reactions you can have. What's with all these, people eating cinnamon? Was there like some cinnamon challenge that I missed where it was kind of cool to see how much cinnamon you could eat? And yeah, doesn't surprise me. I think we all have, siblings that are perhaps not so smart at times. All right, I didn't even know that was a thing. I'm sure if I YouTubed it or Googled it, I'd have millions of people eating spoonfuls of cinnamon. Just the thought of it doesn't really sound that great. The second last one I should say, is surface area. And this one's a lot more difficult to kind of wrap your head around. But kind of once you get it, it maybe is perhaps a little bit easier to understand. So if you think of something in terms of its surface area, so we have to be talking about a solid, generally speaking. And if I look at the blocks down at the bottom here, I have block 1, 2, and 3. So imagine if you had a block of sugar. If I have a block of sugar, like this guy right here, I have 6 sides that are exposed. So if I put that block of sugar in something that was going to react with the sugar, you have the 6 faces that are exposed, but there's all this sugar in the middle that whatever's on the outside can't get to because it's kind of trapped on the inside. So you're limited to the amount of surface area you have in a cube. Now if I took that same block of sugar and took a hammer to it and just smashed it up and just broke it all down, now all of the sugar, it's kind of in a powder now, but all of the sugar that was trapped on the inside of the cube is now exposed. So when you think of surface area, you think, oh, this big block has a lot of surface area. But if I have this powder, that's not as much surface area, but that's not how that exactly works. So if you took all the sides, all the area of the block, and you measured it, that would be a number, let's call it like 10. But if I took all that sugar and hammered it all out and had all this powder, if I took all of the sides of all of those little pieces and added them all up, it would be a lot larger. And I guess this diagram kind of does a pretty good job of explaining it. And the best example I can give you of your sort of everyday life, and next time you're at the drugstore, you can look and maybe you can verify this or not for yourselves, but when you go to the drugstore, there's 2 types of medicine. There's long-lasting medicine, and then there's fast-acting medicine. So these are kind of the choices you have. Generally speaking, all of the fast-acting stuff is going to be, it's always backwards, like this, the powder, these capsules that have a powder in it. So when you ingest it, it goes in your stomach, the capsule, dissolves, and then all of this powder is released into your stomach. So you have a lot of powder and a lot more opportunity for, this to be absorbed and used by your body. But the long-lasting pills are always these kind of solid pills where your stomach acid kind of eats away at the outside of it slowly and exposes more over longer periods of time, and it lasts longer. So next time you're at the grocery store or the drugstore and you kind of walk through the pharmacy aisles, maybe have a look and see if that's the case or not. But this is the idea. A solid pill has a bunch of medicine that's kind of stuck on the inside that won't be exposed for a while. Whereas if it's in a powder, it all is exposed instantly. So that's going to be something that acts a little bit more quickly. The last thing is the catalyst. And the catalyst is, we couldn't live without catalysts. Right now in your body, I don't even remember how many enzymes you have. It doesn't say here. There's literally millions and millions of different catalysts inside your body right now, and your body, we couldn't exist without catalysts. Like basically almost every process that occurs inside any living organism is as a result of a catalyst. And when we do a chemical experiment, we call it a catalyst. When we are talking in terms of biology, a catalyst has a fancy name. It's called an enzyme. You guys have probably heard of enzymes before. So catalyst and enzyme are the exact same thing, just the context is a little different. If we're dealing in chemistry, catalyst, and if we're dealing in biology, it's an enzyme. And they're amazing. And for the simple reason that they just make things line up and reactions happen faster. And you can have the opposite of a catalyst, something called an inhibitor. And an inhibitor is the exact opposite. They're things that make the parts not line up and the reaction not occur quickly. So this little picture behind me, the how enzymes work picture, it looks crazy, but this is kind of exactly what's going on. So basically you have this enzyme where you have this purple thing is what we're calling an enzyme here. And you want the yellow thing and this pink thing to react. But the yellow thing and the pink thing might not be in this particular arrangement when they get close to each other. And if they have to line up like this, they have to be perfectly arranged. You can imagine if the back side of this pink thing lined up with this side, even though they came into contact, the reaction wouldn't occur because they weren't lined up properly. And this is what happens, all the time in nature and just in the chemistry labs and things. So what an enzyme does is it just lines everything up. And it makes everything fit together really nicely. And the fact that they exist at all in the first place just amazes me, but they do. And there's millions of them out there. And literally we would not exist without them. We couldn't survive without the enzymes that are in our body. So enzymes are really, really important to life and chemical reactions. And they make things happen really, really fast. So salivary amylase is in your mouth right now. If you've ever, maybe when you were in grade 7 or 8, you study the human body, you talk about the enzymes in your mouth. If you've ever done this before, you take a piece of white bread and you put it in your mouth and you just let it sit there. And white bread, and when at first you have these really long carbohydrate chains, and basically carbohydrates break down into sugar, and the saliva in your mouth can break down the carbohydrates into sugar. So if you take a piece of white bread, you just put it in your mouth on your tongue, at first it just tastes like bread. If you leave it for a while in there without chewing it or anything, it'll get sweeter and sweeter and sweeter because those really long carbohydrate chains get broken down into sugars. Has anyone done that before? Maybe in elementary school or middle school? No? There you go. Maybe it's a safe home experiment for you to try. Just take a piece of bread, put it in your mouth, see if it gets sweet. And it will, it should. This happens in cars as well. You've probably heard of something called a catalytic converter. And a catalytic converter is just a catalyst for changing, hazardous things that happen in your exhaust, changing them into really kind of environmentally friendlier things. And catalytic converters are full of really precious metals like platinum and sometimes gold, and that's why they're really expensive. And they help convert bad things into good things in exhaust of your car. So catalytic converter just, speeds up the reaction and changes not nice things into nice things. So there you go. These are the things that can speed up or slow down reactions. That's kind of it for the notes. Does anybody have any questions about any of those things? And the opposite is true of all of them. We've talked about, speeding up reactions, but if we wanted to slow down a reaction, we could decrease the temperature. We make something colder using a fridge. If we want to, make a reaction happen slower, we can decrease the concentration of the reactants. And then same deal with surface area. We can increase the surface area to happen slower. And then this last one is the adding a catalyst. The opposite of a catalyst is called an inhibitor. And it is exactly what you think it is. It just kind of slows things down. So I have the same experiment I had last day with the hydrogen peroxide, just because I have hydrogen peroxide here. We don't have a lot of chemicals here because we don't do a lot of chemical reactions and what have you in labs. But so I want to look at the different things that we kind of talked about today in terms of hydrogen peroxide. So I'm going to put on my safety glasses and step over. I brought my own glasses today instead of the super awesome loaner ones from the school. So the first thing we talked about was temperature. What I'm going to do is I'm going to use this really highly concentrated 30% hydrogen peroxide, and I have some of the stuff right here that's been sitting in this ice bath for about an hour. So this is cold. And then over on the side here, I have a hot plate going, and make sure I don't burn myself. This stuff's been sitting on a hot plate. Now I don't know the temperature of it, but it's really hot to the touch. And it's just the exact same stuff. So I'm just going to pull this out of here. And get rid of that. All right, so stuff on my right, this stuff I'm pouring in right now, I'll try to get about the same amount in it. The graduations kind of end down at the bottom there. So this is cold. Hydrogen peroxide. And then this hot stuff is giving off some off gases. You can kind of see the steam coming off of it. So it's definitely colder and hotter. All right. So when this hydrogen peroxide, it would break down naturally into oxygen and water, but what I use is something called a catalyst, and I mentioned it last day, but you guys didn't really think much of it. So the catalyst that I'm using is, you can see that, potassium iodide, and potassium iodide just helps the hydrogen peroxide line up really nicely and break down into its components. Now, if I don't put soap in here, this just splatters everywhere, so the soap's kind of nice to trap some of the bubbles that are produced. So just some regular old sunlight. We'll throw in each of these. It's a lot of soap, but that's okay. All right, so I'll mix them up. All right, so nothing really happening there. Again, this guy over here is hot. This guy over here is cold. And I have some potassium iodide that I just dissolved in some water. I'm just going to switch these. So I'm just going to pour a little into each, and we'll see which one happens faster. Now, hopefully the hot one happens a little bit faster than the cold one. I need to be careful. I don't know if I'm going to be able to pour these both at the same time, but we'll see. Ready? Whew. All right, so you can see the hot one kind of explodes, and the slow one going slowly. So that gives you an idea of, obviously this guy over here on this side happened a lot faster, just kind of shot right out almost instantly, whereas the cold guy happened a lot slower. But still fast, because we use that catalyst to kind of speed things up. All right, that's the first one. I'm going to do the same thing again with concentration now. Oh, these gloves aren't so great. I brought my own glasses, but I forgot my gloves. All right, so I'm just gonna get these out of the way. Think of how to do this without. There we go. All right, so grab 2 more cylinders here. Just move some of this stuff out of the way. All right, so this is hydrogen peroxide from the grocery store. What happens if I keep it closed? It will, it'll explode. We probably don't want that. All right, so the stuff from the grocery store is, as I mentioned before here, it says it's 3%. So I'll put some of that over here on my left. So there's some 3% hydrogen peroxide. And then on the other side, I'll get some of the good stuff here. I'll use the warm stuff again because that's... All right, so my right 30%, my left, my left is the 3%. I lost my soap. There it is. All right, so this is just a direct comparison of 30% to 3%. So you would assume that because the more concentrated something is, the more hydrogen peroxide is actually in here. So 30% of this side is hydrogen peroxide, whereas this side, only 3% is hydrogen peroxide. So I'll just do them one at a time because it's not going to really be that exciting over here. So this is the 3%. And you can see the reaction is happening fairly slowly. The decomposition here doesn't actually happen very quickly at all. You can see it kind of just bubbling away at the bottom. If I just pull this out of its stand. There you go. Mr. Ross is a magician with the camera. You can see it bubbling away. So it's just kind of happening. It's going. Not in any particular hurry. So that's what 3% looks like. And it'll just eventually kind of rise up the cylinder and overflow. Now we've already seen what 30% looks like, but I just love doing this stuff, so I'm just going to do it again. So this is 30% again. Kind of ruined it for the 3%. So you can see that obviously it happens a lot quicker because it's more concentrated. Meanwhile, the 3% still climbing up there. Slowly but surely. I think we should just note here that having these reactions occur quickly is good for you guys again. Make it a cannon. What do you pour into it to make it go boom? That's the potassium iodide, and it's just a catalyst constant. It just basically lines up the H2O2 and makes it break down faster. I don't know if you can get potassium iodide in anything. A lot of times when we have these fancy chemicals that we use, we buy them from companies that produce chemicals for the sake of scientific experiments. And they have fancy names like potassium iodide and stuff like that. But really there's usually common stuff that, like hydrogen peroxide is the common name, but it's H2O2, so it's actually dihydrogen dioxide. Is his chemical name. So there you go. So that's that. I meant to grab a Erlenmeyer flask because those ones work really good in terms of getting some serious height out of this. We should fill the entire room with this. When you get this stuff, you can see on my gloves here probably, the iodine and the potassium iodide, it stains these gloves. So it turns your gloves into this really brown color. And if I get it on the white paper in front here, you can see it stains it that kind of blackish color instantly. So I use gloves not because I'm really scared of the stuff touching my hands. Remember these bubbles are just oxygen gas and then sunlight, and that's it, a little bit of water in there. So it's nothing harmful, but the potassium iodide that I'm using this dissolved in water. It has that kind of yellow tinge to it. Once the reaction occurs, some of the iodine starts to come out of solution, and you can see it starts to turn this yellow color, and if I touch anything with it, it turns that black. So if I filled the entire room with this stuff, I would be like an orange person. It would look like an Oompa Loompa for the rest of the week until my skin fell off. Do I have one more? I do have one more. Just trying to think. I got some hydrogen peroxide out, so I guess I just have to use it anyway, so I'm just going to throw these both onto one here. And we'll do one more time just for fun. All right, so what do we figure? Do you want it to happen really slow or really fast? We'll do a bunch of it, so just make a huge mess. Fast is good sometimes, but it's fun when it happens really slowly because it'll just keep going and going and going forever, which is quite interesting. Fast. Okay. So again, without the soap, it just kind of splatters everywhere. At least the soap actually had to cover the top. If you fill it all the way up, it does the same thing. It just makes a bigger mess, and I have more cleanup at the end of the day, which, I don't know, doesn't really sound that fun to clean things up. So before I do this one, well, maybe we'll do it and then we'll come back. I'm just going to put a couple drops of the catalyst in, and we'll just kind of watch what happens. So normally I put a lot of the catalyst in, but we'll just kind of go a couple drops this time. So you can see it'll just kind of keep going. The catalyst isn't getting necessarily used up in the reaction, it's just there. It's not actually part of the reaction. So you can see the hydrogen peroxide down at the bottom, kind of bubbling away. It'll keep coming out, and it'll just keep dropping lower and lower and lower as it kind of comes into contact with the catalyst. Get this stuff out of the way. So it just kind of keeps oozing out the top. It'll just keep kind of going and going. A little bit more of the cold stuff here. I'm just going to throw it on a hot plate for a second. I grab an Erlenmeyer flask and I'll see if I can get it to shoot out pretty high. When I was at OKM, I did this experiment. I grabbed somebody had recycled like a 1 liter pop bottle in the hallway recycling. So I went and grabbed it, and because the nozzle on the pop bottle kind of goes up and in, it worked exactly as like a jet would. That's kind of how jets are designed. They take some pressurized gas and then they convert it into like a really small area. And it actually came flying out of the top, and I kid you not, on the ceiling it had those white ceiling tiles. And in the room that I taught at OKM, there's still a really brown stain up on the roof from the experiment I did. I'm just going to throw a little bit more in here just to react it all. Okay. Just give me 2 seconds. I'm just going to run and grab a flask from the other end of the world, and I'll come back. Of course, I got iodine bubbles on everything. I'll be back. All right, thanks guys for waiting. So I have this Erlenmeyer, and we'll pour some whatever we have left here. Unfortunately, I don't have a lot of the hot stuff left. In order to get it to go really high, I need to get it almost boiling. But this one done, almost done. All right, so the last, I said I'd show you this too while we're here, while Mr. Ross is doing this. So this is that copper 2 chloride that we had last day. And you can see on the kind of the front, you have that all the copper at the bottom, because the aluminum foil's all gone now. And what's left is just copper in the bottom there. And you'll notice that blue color is still there a little bit. So the majority of that solution now is, it's no longer copper 2 chloride, now it's aluminum chloride. So if we wanted to reverse the reaction, we probably could, and we would end up with aluminum coming out of the solution. Looks like there was something, you can tell when people clean their glassware really well or not. This has turned a yellow color, so there was something in there that shouldn't have perhaps been in there, didn't get cleaned out last time. All right, so that stuff in there is a bit warm. I'll add a little bit more of this from the bottle. And the bottle we keep in the fridge to slow down the reaction. There we go. There's a lot in there. Add our soap to trap the gas, the oxygen bubbles that are produced. This is the smallest one I could find. Unfortunately, it doesn't have a really small nozzle on the top, so it's not going to shoot out too high, but it should be okay. And I don't know why it turned yellow, which is kind of concerning me a bit, so there's probably something in there. I don't know what it is. So if we all disappear, you'll know why. And then I'll add all of my catalyst at once. We'll see what kind of height we can get out of this thing. If I can get it out of frame, no worries, Costin. We're done, Costin. There's nothing important left whenever you want to go. So we'll see how high this goes, but I'll pour in all of the catalyst. Oh, that's not bad. Didn't get the height I wanted, but we got the volume there. Now I have to clean it up. So anyways, I like playing with it because it's fun. It makes a huge mess though. And that's decomposition of hydrogen peroxide, H2O2, with your potassium iodide catalyst, speeding up reactions and slowing them down and what have you. So there you go. You can really see the steam coming off this. It gets very warm, so it's a very exothermic reaction. Thank you, Kyla. Anyone want to come in and help me clean? Now my hands are all stained brown and whatnot. So there we go. Thanks very much, guys, for being patient with me today. The Unit 6 stuff's done. There isn't really a ton of stuff there to begin with. So I know you guys were having a little bit of concern about the types reactions from last day. So what we can do is we'll start next class. We'll maybe go through the rest of the questions on there. Maybe balance a few of them just so we get a little bit more practice with that. Essentially, Unit 6 is done though. So we'll aim to have the Unit 6 test done kind of mid next week. So you have the weekend to kind of go through and clean it up and figure out what's what and where you're having issues. And then we'll finish up Unit 6. We're going to go into Unit 5, which is just more chemistry, acid, and base stuff. And again, Unit 5 is pretty short. There's not a ton of stuff there. Unit 5 is good because we refer to the data booklet a lot, so there's not a bunch of stuff to memorize. It's kind of reference to the data book. So that's where we're going. We have Units 5. Unit 7 is radiation, which is a pretty cool unit, and it doesn't really take that long, maybe a couple weeks. And then we have the 3 physics units, which are very, very short as well. So we're pretty much you know, fairly close to being done the course here. There's not a ton of time left, about a month-ish, and I know Mrs. Wood put up final exam dates on the homepage. I think it's the 20th for socials and the 21st for science. We'll have to double check that, but I guess I could look. They're up here. What do we got here? So Friday, June 16th is the last day to submit things. And then the 21st is your social studies exam at 9 o'clock here at McWilliams. And then on 22nd, that's your science exam, again here at McWilliams. So 2 days in a row. So that's where we're at. If you haven't done Unit 4, that needs to be, you know, finished and submitted. Hopefully you can get that test written before the weekend. If you get it into me today, I should get it marked and back to you with the password. Then on next week, we're going to have 2 classes again. We'll probably finish up Unit 5 next week. So if you're kind of hesitant on Unit 6, you got to just kind of, you know, power through this stuff. So we'll start next day with some Unit 6 stuff, but we'll also move on to Unit 5 because it won't take another hour and a half to go through all the Unit 6. So that being said, in the course, you're going to have to print off the Unit 5 learning guide, and I'll go open that up right now when I get into my office. So Unit 5, we'll start on Tuesday's class. We're sailing tomorrow at the sailing club if you'd like to join us. It's supposed to be kind of, you know, rain on and off, or showers. Hopefully it's nice. We're there for the full day. They have covered places to hang out and whatnot, and you're out in the water, you kind of get splashed a little bit anyway. So it's really fun. You just kind of sit around on the boats and go sailing. It depends on the weather and how windy it is. If it's raining, it probably won't be windy. And bring a change of clothes, bring a lunch. It's just a good opportunity to just kind of hang out down on the beach for the day. You know, it might not be the best looking day tomorrow, but it's pretty low impact. You don't really need to know anything, and just kind of hang out in the sailboats. So it'd be great to see a few of you guys there tomorrow. I hope you guys have a great afternoon and a great weekend, and I'll see you for sure on Tuesday. Thanks very much, and take care.